Good morning, one and all. I am Dr. Ramya Swetha, Civil Engineering Department from Institute of Aeronautical Engineering. Today, our topic is boundary layer theory. Coming to the boundary layer theory, these are some of the web references we may consider for understanding the boundary layer and their parameters and how it works and what are the important parameters involved in boundary layer and new terminology also we may understand using these web resources. In these web resources, this is available in terms of PDF, this is available in terms of PPT, this is also in terms of PPT. So these are the web resources we may consider for understanding the boundary layer theory. Coming to the boundary layer theory, it is a concept which belongs to the fluid dynamics. It is not in rest state, not in the kinetic state of the fluid. The boundary layer theory is concept on fluid dynamics. We cannot consider boundary layer in fluid at rest condition. It means fluid static and other formation of fluid is fluid kinematic. So those two conditions, those two fluid characteristics are not applicable for boundary layer theory. It is a concept for fluid dynamics that refers to the layer of the fluid closest to a surface over which fluid is flowing. So fluid closest to a surface, boundary layer. So whenever the fluid is there, in most of the cases it is water we are considering. So in the water, any obstacle or any object is going to move in that surface of the water. So because of that movement of the object, because of that velocity of the object, based on that, what are the parameters, what are the parameters are going to be influenced because of the object moving in the surface of the water. For example, boat, like that, boat, ships. These are some of the examples for understanding the boundary layer. So first we have to consider the surface. So the fluid closest to the surface of the flowing fluid. So in that, any obstacle is moving, any object is going to be moving in the above layer of the surface. So what are the parameters are going, what are the things are happened closest to the surface? So that this is nothing but the boundary layer. So inside, whenever we are going to, the depth is going to be increased. So it won't affect the velocity, whatever the effects are happening because of the object moving in that surface, that is going to reduce. So in the above, what is going to happen? The complete understanding is nothing but the boundary layer concept. So this layer is characterized by a gradient of velocity. So the layer which is characterized by gradient of velocity. So it depends how the object is moving, what are the various conditions. For example, normal boat which is driven by a person, and some motor boats, like that we may understand the difference. We manually, one person is used to pull that rod. Such kind of boats and such kind of boundary layer characteristics, those gradients, those fluid properties are varies whenever we are using the one motor for moving the for movement of the boat. We are using machinery and we are using manually. Like this, the variations we may understand. So this is the one of the example we may understand. So in that, characterized by a gradient of velocity and other fluid properties such as temperature and pressure that changes as one moves from the surface to the main flow of the fluid. So sometimes we may, the object, whenever the boat or whatever the object which is moving opposite to the flowing fluid, and sometimes it may along the direction of the fluid. The object is moving along the direction of the fluid. The object is moving opposite direction of the fluid. In some cases, the object, so this, whenever it is considered as a river, it is the object. So the river is flowing like this. This is the direction of the river. Just for example, the object is moving like this. So the pressure and the way of changing of the moves, and from here to here, the same object, to consider two same objects within the same length of the channel, we are considering. So within the same length of the channel, so same kind of object which is opposite, the direction is opposite to the direction of the flowing fluid. These parameters are going to differ than the same object which is moving in the same length of the channel along the flowing of the fluid. So these are the, so the movement, so it reaches its destination, for example 1 kilometer. So same speed, same capacity of the boats we are considering within the same channel along the direction and opposite the direction of the flow, it takes different time. So the parameter is going to change. So all these parameters we are going to understand in boundary layer theory. So in this, so based on the fluid properties, temperature, pressure that changes as one moves from the surface to the main flow of the fluid. So the study of boundary layers is important in range of applications such as aircraft design, oceanography and chemical engineering. So these are the important applications. These are the boundary layers important applications. The study of the boundary layers is very important in these particular applications. As coming to the hydraulics and hydraulic missions, we have to understand in hydraulics in water point of view, in flowing liquid point of view. So boundary layers can have a significant impact on the performance of fluid systems, including drag reduction, heat transfer and mixing efficiency. These are all the significant impact systems we are going to understand in fluid systems point of view. So this is, the concept is completely based on the fluid dynamics, which refers the closest portion of the flowing fluid on the surface of the flowing fluid. Now, so like this. So the drag on a body passing through a fluid may be considered to be made up of the two components. So the one is form drag and the second one is skin friction drag. Form drag and skin friction drag. These are the two important components through a fluid may consider to be made up of the body passing through a fluid. So coming to the form drag, which is dependent on the pressure forces acting on the body. So which is dependent on the pressure forces acting on the body, and the skin friction drag, which depends on the shearing forces acting between the body and the fluid. So form drag and skin friction drag, these two are the important components. Coming to the form drag, this pressure forces acting on the body. Pressure forces acting on the body. Pressure forces acting on the body. Coming to the skin friction drag, Coming to the free skin friction drag, which depends on the shearing forces. Shearing forces acting between the body and the fluid. Between the body and the fluid. This is the object, this is the body, and this is the fluid. This is the fluid. So like this, we are understanding these two components. Coming to the shear force and pressure force. So major laws, coming to the shear forces, viscous drag, frictional drag, or skin friction. Both are same. Whether it is called it as frictional drag or skin friction. Viscous drag and frictional drag caused by shear between the fluid and the solid surface. Solid surface. Both fluid and the solid surface. Function of surface area and the length of the object. This is nothing but the shear forces. So surface area and length of the object. How much the length of the object is there? It depends upon the how much the length is going to the how much the length of the object. It may more or less whatever it, how much the length of the object moving on the particular fluid, in that fluid. Then the length of the object, function of the surface area. How much surface area of the fluid is going to be occupied by the object. So based on the how much the surface area is occupied the object, and so these are the parameters which for understanding the shear forces. Coming to the pressure forces, pressure drag or form drag, both are same. Form drag or pressure drag. This is pressure drag or form drag. In most of the cases, we are considering it is as pressure drag. Pressure drag or form drag. So coming to the pressure forces, the pressure drag caused by the flow separation. Flow separation from the body. So the flow separation from the body, function of the area normal to the flow projected area. Projected area. So these are the two forces we are going to understand in this boundary layer theory. Coming to the description of the boundary layer, these shear stresses, wall shear stresses. So these shear stresses in the immediate, whenever the body, the velocity of the fluid increases gradually from zero at boundary surface to the velocity of the mainstream, this region is known as boundary layer. Where we are considering this particular boundary, whenever it increases, the velocity of the fluid increases gradually from 0 to at boundary surface to the velocity of the mainstream, from 0 to whenever it is considered. This is the delta we are considering for this, that particular region. Whenever it changes from, increases from, velocity of the fluid increases gradually from 0 at boundary surface to the velocity of the mainstream, this particular region is known as boundary layer. Large velocity gradient leading to appreciate the shear stress. It depends upon the shear stress. Basically, shear stress is equal to mu dou u by dou y, where y is equal to 0. Where y is equal to 0. The nominal thickness of boundary layer is defined as the distance from the boundary where the velocity of the fluid is 99% of free stream velocity. This is the definition for nominal thickness of the boundary layer. Nominal thickness where the velocity of the fluid is 99% of the free stream velocity. Free stream velocity, that is nothing but that is known as nominal thickness of the boundary layer. Nominal thickness of the boundary layer. Boundary layer theory. When coming to the boundary layer theory, so whenever the real fluid flows over a solid body. So till now I used the term for object. So coming to the as per definition, when a real fluid flows over a solid body, the velocity of the fluid at the boundary will be 0. So whenever the real fluid, let's consider water. So water, whenever the water is flowing over a solid body, the velocity of the fluid at the boundary will be 0 if boundary is stationary. If boundary is stationary, as we move away from boundary in perpendicular direction, along the perpendicular direction. So as we move away from boundary in perpendicular direction, velocity increases to the free stream velocity. So that velocity, the direction velocity increases to the free stream velocity. It means velocity gradient is dou u by dou y. Velocity gradient du by dy will exist. Whenever we move away from the boundary in perpendicular direction, velocity increases to the free stream velocity. It means the velocity gradient will exist. That velocity gradient is nothing but du by dy will exist. The velocity gradient du by dy does not exist outside the boundary layer, as outside the boundary layer velocity is constant. That means outside the boundary layer, which is velocity gradient does not exist outside the boundary layer, as outside the boundary layer the velocity is constant and equal to the free stream velocity. If along the direction of the velocity increases to the free stream velocity, that to the boundary whenever we move from boundary to perpendicular direction, velocity increases to free stream velocity, it means velocity gradient will exist. Du by dy, velocity gradient does not exist outside the boundary layer, velocity is constant and equal to the free stream velocity. These two parameters, these two variations we have understand very clearly. Okay. Now, so this is the variation between whenever, if the velocity gradient does not exist, what is the condition, and for the particular condition, it means the velocity gradient will exist in boundary layer theory. So this is the free stream velocity. U is equal to 0, velocity is equal to 0, U is equal to U ultimate. So from this to this, we are considering the boundary layer, this region. This is the boundary layer for theory. Whatever till now we understand theoretically, this is the representation. This is the graphical representation. This is the free stream velocity. So U is equal to 0, U is equal to U unlimited. So this is the region. We are considering the boundary layer. So this is the free stream velocity. This is the boundary layer theory. In this, whenever the velocity gradient is existing, the perpendicular direction as we move increases the velocity. It means the velocity gradient is existing. It does not exist means, it means the velocity is constant and it is equal to the free stream velocity. So this is the concept. Now coming to the development of boundary layer theory. Development of boundary layer. So it depends upon whether it is belongs to laminar, turbulent. First we have to understand whether it is belongs to laminar or turbulent. So first we have to understand and we have to know about these transition periods, these different layers: laminar boundary layer, transition region, turbulent boundary layer. So after going through the transition zone of the finite length, the flow becomes completely turbulent, which is characterized by three-dimensional. After going to this region, coming to this region, so which is characterized with three-dimensional: random motion of the function, fluctuation induced bulk motion parcel of the fluid. So laminar boundary layer profile is parabolic. Turbulent boundary layer profile becomes the logarithmic. So because 3 dimensions are going to involve. So how it is, the development is done, we will observe in this. So development of the boundary layer can be divided into 3 regions. The one is laminar, transition and turbulent. So once the laminar turbulence is coming anywhere in the fluid mechanics, the Reynolds number comes into the picture. So based on the Reynolds number, rho v into x by mu, that is equal to mu into x into mu. So this is the Reynolds number. This Reynolds number is less than 5 into 10 to the power of 5 for flat plate if this is known as laminar boundary layer. Whenever the Reynolds number is less than 5 into 10 to the power of 5, that too for flat plate, this condition belongs to the boundary layer for laminar boundary layer. Laminar boundary layer. Coming to the if the Reynolds number is more than the 5 into 10 to the power of 5, such type of flow is turbulent. So like that we are going to development of the boundary layer divided into these regions. Now in this, the boundary layer depends on Reynolds number and also on the surface roughness also. The development and the boundary layer depends on Reynolds number and also surface roughness. Coming to the roughness of the surface adds to the disturbance in the flow and the transition from the laminar to the turbulent. Coming to the for laminar flow, tau shear stress is equal to mu dou u by dou y. For turbulent, this is the Ide viscosity. This is Ide viscosity and is often much larger than mu. It is. So now coming to this boundary layer. So this is the boundary layer thickness. This is the boundary layer thickness delta. Coming to this velocity, this is the boundary layer V, and like this the flow is like this. Coming to this and little bit. Coming to the turbulence. So this is the turbulent layer over overlap layer, viscous sub layer. These are all comes under in this development of boundary layer like this. So this is the like this and this is the transition. This is the turbulent region X from the leading edge in the horizontal direction. Boundary layer thickness for laminar and turbulent. The boundary layer thickness is governed by the parameter like incoming velocity, kinematic viscosity of the fluid, etc. These are the parameters which are depends upon the boundary layer theory. Boundary layer is theory. So now delta laminar is equal to 5.0x root REX for laminar. Coming to the for turbulent, this is the formula for boundary layer thickness 0.377x by Reynolds number whole the power of 1 by 5. This is for laminar flow. and turbulent flow. Layer thickness. So it is the distance from the boundary to the point where velocity of the fluid is approximately equal to 99% of the free stream velocity. It is denoted by delta. So this is the boundary layer thickness. Whenever the boundary layer region we are considering that velocity is equal to 0 to 99% of the free stream velocity, it is represented. This is layer thickness. It is the distance from the boundary to the point where velocity of the fluid is approximately equal to 0.99 of the free stream velocity. Free stream velocity. This is free stream velocity. Based on the free stream velocity, we are representing the layer thickness. Layer thickness. So now displacement thickness. Delta star. It is observed that inside the boundary layer, velocity of the fluid is less than free stream velocity. Whenever coming to the displacement thickness, delta star, it is observed inside the boundary layer velocity of the fluid is less than the free stream velocity. Hence, discharge is less than in this region. It means, so coming to the inside the boundary layer velocity of the fluid is less than the free stream velocity. It means discharge is less in this region. In the particular region, discharge is less. So to compensate for reduction in discharge, the boundary is displaced outer in the perpendicular direction by the some distance. So the discharge, whenever the discharge is going to less in that region, it is going to compensate for reduction in the discharge. The boundary is displaced outward in the perpendicular direction by the some distance. The some distance is called displacement thickness delta star. So whenever we are observed inside the boundary layer velocity fluid is less than the free stream velocity, hence discharge is less. For compensating this discharge, the boundary is displaced outward in perpendicular direction by some distance. That particular some distance is nothing but the displacement thickness. Formula for this displacement thickness is integral 0 to delta 1 minus mu by mu into dy. Coming to this, here we are going to understand this is the boundary layer, this is the free stream velocity. Whenever the particular some distance with respect to this is the y. So along this direction. So like this is the width of the plate. Consider the small portion. So like this portion is, this is the section for this. So this is the boundary layer thickness from 0 to delta 1 minus u by u whole the power of with respect to y. So this is the displacement thickness. Boundary layer reduction in velocity occurs. Momentum also reduces whenever the momentum thickness is defined as distance measured normal to the boundary of solid body by which should be displaced to compensate for the reduction in momentum flowing fluid. So theta is the denotation for the momentum thickness. The next one is energy thickness. This energy thickness is denoted delta stars or 2 stars in this. This is the denotation for energy thickness. Coming to the definition of the energy thickness, it is defined as the distance measured which is perpendicular to the boundary of solid body by which the boundary should be displaced to compensate for reduction in kinetic energy of flowing fluid. So the energy thickness, this is from the kinetic energy. So the kinetic energy decreases due to formation of boundary layer. So because of the formation of this boundary layer, kinetic energy is going to decreases. So this decreases, we are going to the reduction, how much the reduction happened in kinetic energy in that particular flowing fluid. For that compensation, for compensate the displacement, that should be in measured distance but perpendicular to the boundary of a solid body. Such is nothing but the energy thickness. So these are the parameters which we are going to understand in our boundary layer theory. So in this, momentum thickness and displacement thickness and layer thickness, these are the various parameters which are included in our boundary layer theory. This layer thickness is denoted with respect to delta, and it is and the definition we know already. We discussed this definition. The next one is the displacement thickness. The displacement thickness which is observed based for the velocity point of view, for compensation of velocity. Coming to the momentum thickness, whenever the momentum also, so the momentum is also decreases. Here the displacement is velocity, momentum, it comes under momentum. Energy thickness, it represents the kinetic energy. The name itself tells this, which the relevant of the parameter, the particular parameter. Energy, kinetic energy, momentum, displacement, that is from velocity. We know displacement, velocity is equal to displacement by time. We know the definition of velocity, displacement by time. So based on that, so whenever we are getting the definition or the exact parameter gives the details. The momentum thickness itself is denoted theta. These are the parameters which we are going to understand, and these are the formulas for finding the energy thicknesses, momentum thickness for boundary layer theory, displacement thickness, momentum thickness, and energy thickness. Thank you.